EMF induced in a moving conductor. We have two ways of changing the flux here. We can increase your magnetic field, that will change the flux, or we can change the area that the magnetic field acts through. So here we have a loop of wire, and this continues out to the right for some distance. We have an external magnetic field that is pointed out of the picture. The length of this wire, this dimension is L, and we have a metal bar here which is a conductor that is sliding at a constant velocity on this blue line here. We want to find the changing area here, which is going to lead to a change in magnetic flux. Well, the area is the height here, which we call L. We have L. And then we want to find what happens here if we're moving at a velocity v. Well, we know that velocity is defined as displacement over time. So the displacement here is going to be v delta t. So I now have v delta t is this increasing length, and I have L here. So the changing area will be L times v delta t. Use Faraday's law now to find the EMF induced in the circuit that contains, here we have the conducting rail, and we have the bar, which is moving like that, and that's going to induce an EMF, which will drive a current through this wire here. So Faraday's law is minus n delta phi over delta t. There's only one loop, so n is equal to 1. B is constant, so we pull B out over here, and then we have delta A. We found that delta A was LV delta t. We cross out the delta t, and we find that the EMF is negative the strength of the magnetic field times this length here of the wire times the velocity at which the bar is moving. What is the meaning of the negative sign? That tells us that the induced EMF is in the direction that creates a current that will generate a magnetic field that opposes the increasing magnetic flux. So what that means is here's our setup. Here's the wire, and then we'll move the bar out here, and it's moving to the right. And the magnetic field, the external magnetic field, is coming out of the board. As this bar moves to the right, we have a greater flux due to the magnetic field because of the greater area. So we want to decrease this magnetic field. So how do we do that? Well, let's use a different color here. We'll want to generate a magnetic field going into the board. So we reduce that flux. So which way would current have to flow in this wire to get a magnetic field like that? You would use your right-hand grip rule, and then that would tell you that the current flows this way in the clockwise direction. Another way to look at that is the direction of the induced EMF is necessary to be in agreement with the law of the conservation of energy. And we're going to prove that by assuming the opposite. So here's the bar, and it was moving at constant velocity when it was in this field. And we showed on the last page that it will induce a current that is going this way. So we will have a magnetic field within the loop into the page, and that will help cancel out the increasing flux due to this magnetic field. Let's say the current went in the other direction. Let's say it did go counterclockwise. That would create a magnetic field out of the page within the loop using the right-hand grip rule. So you would increase the magnetic field, which would increase the flux, which would then increase the velocity of this object. So the bar would keep moving faster and faster and faster with no external force, which violates the law of the conservation of energy. So we know that the bar can't speed up without an external force. That would be violating the law of the conservation of energy. So let's look at what's really happening here. Here's our loop, here's our bar, and it's in an external magnetic field like this, and we said it's going to generate an EMF that will have a current flow down like this through the bar. Well, if you now use the second right-hand rule, if I have a current flowing down and I have an external magnetic field out of the page, that's going to apply a force on the bar in this direction. So if we just gave that bar a push and got it moving, it would eventually slow down. The force on the current here would be in this direction, which opposed our initial force. So eventually this thing would stop. So if you wanted to keep this bar moving and generating a current, you would need to apply a constant force to the bar. You would have to keep pushing it so you could generate the EMF. The next few slides will go into this force derivation of the EMF, a different way of looking at it, and with any luck we'll get the same answer as the BLV that we just did. The rod is pushed to the right. We will use the right-hand rule to find out the direction of the magnetic force on the positive charges in the rod. So the velocity in this direction, magnetic field is coming out of the board, there will be a magnetic force on the positive charges moving them down to the bottom. And you can see we have this plus here, and as the positive charges go here, they leave behind a negative charge up here. Well, what do we have now? We have a separation of charge. So we now have an electric field in the rod pointing from bottom to top. So there will be an electric force on these positive charges counterbalancing the magnetic force. This will go on until these two forces are equal, and then the charges will stop moving. So in equilibrium, the sum of the forces in the vertical direction will be the electric force due to the electrical field that is generated by the separation of charges, and a magnetic force due to the movement of the bar through the magnetic field. So F sub E minus F sub B equals ma, Newton's second law, equals 0. We'll continue the derivation. The sum of the forces is the electric force minus the magnetic force equals 0. The electric force on a charge is QE. The magnetic force on a charge is QVB. Continue the math, the Q's cancel, and we get the electric field is V times B. Now the two ends of the bar produce a constant electric field, very much like the parallel plate capacitor. Remember that? Where we had this, the electric field between the positive and negative plate, and we found out that the voltage difference is minus the electric field times the displacement. So here, our maximum distance here is L, so EMF will equal voltage equals minus EL. E therefore is minus EMF over L. Substitute again into this equation, and we get EMF is minus BLV, just like before, using Faraday and Lenz's law. Find the direction of the induced current in the loop. The bar has a net positive charge here and a net negative charge up here. So when we connect it to a conducting wire, like so, charges will flow from positive to negative. So this is giving us a clockwise direction, which is the exact same result we obtained with Faraday's law and Lenz's law. A 15 centimeter wire moves at a constant speed of 6.5 meters per second perpendicular to a uniform magnetic field of 0.80 Tesla. What is the induced EMF in the wire? We write the givens up here and be sure to turn 15 centimeters into 0.15 meters. Here's our velocity, here's our magnetic field. We use the motional EMF equation, BLIV, and here's our magnetic field B, here's L, and here's the velocity. So our EMF is 0.78 volts. How strong must the magnetic field be in order to induce a 6-volt EMF in a 0.32 meter wire that is moving at a constant speed of 17.2 meters per second perpendicular to the field? Use the motional EMF equation over here, and we need to solve that for B, and we do that by dividing both sides by L and V, substitute in our givens, and we get a magnetic field of 1.1 Tesla.